So all this assumed that we had a square thread. This lambda here, this angle lambda, was only because of the helix angle. That's the lead angle. It's because when we unwound the helix, we found that the path that we were going up was at an angle relative to horizontal. This had nothing to do with the teeth being angled. This is just true for a square thread. I've drawn these as square threads. Now there's other thread shapes out there. For instance, there's ACME threads, and those can be used for lead screws as well. It turns out that they're easier to manufacture. We'll see soon that they're less efficient, but they're easier to manufacture. And so instead of, we're going to have a little bit different geometry that we need to take into consideration. Now this is an approximation, but it helps us see why square screws are more efficient in the long run. All right, so let's figure out why we're going to have more friction with this ACME type screw. So I'm going to draw a little diagram here. It's going to show an ACME thread. Sort of looks like this. This is one side of the ACME thread instead of the square thread. Okay. Doesn't matter what happens over here, doesn't matter what happens over here. I'm only going to interest myself in this face right here. I'm just going to look at this part. I'm going to cut this out and analyze this. Or you can say I'm analyzing all of the surfaces at once. And it's over all that area. But all of it has this same angle here, this same angle. And this is the thread angle alpha. So in our equations before, when we drew this diagram, we said that if the lead angle lambda were 0, then the normal, like in this case, because we had square tooth, the normal, the force N, was going to be equal to F. Imagine that this tooth shape has no lead angle lambda. So it's no longer a helix. It's just wrapping around in circles. In this case, though, you do have a normal force that's greater than F that you apply here. So let's zoom in on just this portion. Let's draw the free body diagram for that thing. The free body diagram for this here, I'm going to draw it just as a triangle, but it's basically like we're analyzing all the surfaces of all the teeth at once, or the entire tooth wrapped all the way around. So this is our force F, and we've got a normal force that's acting in this direction. We actually also have an additional friction term, right? We've got a friction force that as we turn this, then we've got a friction force that's kind of out of the board, and that's going to be mu times N, right? So I guess if we're turning it, maybe the friction force is into the board if we're turning it with a positive torque in this case, then this surface is going to have a friction force that's going into the board, mu N. So this normal force is not equal, so because of this angle alpha, let's draw that. This is alpha. Because of that, let's do the sum of forces vertically on here. The sum of forces vertical is N times, again, cosine of alpha in this case, because if alpha were 0, cosine of alpha would just be 1, minus F, and that has to equal 0. This friction force into the board is not going to affect anything. So our normal force is equal to F over cosine alpha. That's equal to F times the secant of alpha. That's going to increase our friction. And so the argument goes that wherever you see a friction turn up here, what you can do to take into account, even for non-zero lead angles, is just multiply your friction coefficient by a secant of alpha and adjust these equations accordingly. So this one becomes F dm over 2 times L plus mu pi dm and the mu gets multiplied by a secant alpha over pi dm minus mu L secant alpha. And likewise, this one becomes f dm over 2 pi, or mu pi dm secant alpha minus L over pi times dm plus mu L secant alpha.